Good morning, dear friends. So as per the previous classes, we have discussed regarding the design of tension members. Next, we have seen some problems also as per the analysis. Means we have seen some example problems, exercise problems on analysis of tension members. What is its resistance capacity towards a section given. Today we'll do problems on design of tension members, that is design. First, before going to the problems, we'll try to see design steps for tension members, design steps involved in a tension members. So for that, first, based upon the given data, if load is given, if a working tensile load P is given, you convert into factored. So as per limit state design, factored load PU equals to 1.5 into working load. This is the first step you have to do. Sometimes in problems they will be clearly mentioning design a tension member for a factored load. In those situations, no need to multiply with 1.5. okay. In case if it is not mentioned, it is nothing but called as considered as a working load. So to that working load, multiply with 1.5, you will be getting the factored load. Okay. Now second one, I said you earlier also, while performing the design you are supposed to make some assumptions. So here you are supposed to assume permissible tensile stress, permissible tensile stress, okay, in the section. Now how it is denoted? It is denoted by FTD, okay, which is equals to, you can take 90% of yield stress. Okay. Next, third one, after that one, after assuming this one, calculate the area of the section required. Area of the section required equals to PU by FTD. Now you will be getting the area in this area thing from this one. For factor of safety, increase the area, okay, by 10 to 25%. okay, whatever the area you got, to that area you increase by 10 to 25. How to get? Suppose if I am increasing, if increase by 10%, then the area required will be equals to area got in third step multiplied with 1.10. you will be getting the area required. Okay. Now from steel table SP6, okay, steel table, based upon the area required you obtained here in step 4, you choose a section. Okay. Now what section you have to choose? It depends. How? Suppose if in a problem, if they clearly mentions about the design a equal angle section or design a unequal angle section, okay, like that, if anything is separately mentioned in the problem, in that situation you have to definitely go with the given data. Design a equal angle section means you have to choose the section from the equal angle sections called tabular column only. If it is not mentioned, just design a angle section for a roof truss, if they mention like this, means in that situation you can go either with respect to equal angle or unequal angle. Okay, that is the section choosing. After that, I said you, after choosing the section, whatever the process we done in analysis, what we do, we will be determining the design strengths, okay, due to what, with respect to cross section yielding, net section rupture and block shear failure. Okay, so the least will be what, the design strength of this, least from above 3 will be the design strength of the test member. Okay, next, suppose if the strength obtained from where step 6 is greater than step 1, that is what, PU or PD, or PU, this is PU and this is PD, then what you obtained is correct. If at all the value obtained in step 6 is less than this one PU, then in that situation what happens, you have to redesign the section. Okay, and you have to go for the last one, check the section for what, slenderness ratio. Check the section for slenderness ratio. Okay, so any design problem pertaining to tension members, these are the following steps. What is that? Based upon the given data, if the load is factored load, no need to multiply with 1.5. If it is a working load, to get a factored load, multiply with 1.5. That is the factored load. Next, you have to assume the permissible tensile stress in the section of what, 90% of the yield stress of the material. So that is 0.9 into F5. Next, area required will be equals to the load, factored load by permissible design tensile stress. You will be getting what, area required. You increase that area about 10 to 25% in between, you as you wish. So for that you will be getting the required area, incremental required area will be getting. So for that area you choose the section from the table. Now how to choose the section, I have mentioned you that if it in a problem, if they mention separately that design a equal angle tension, means you have to search for only equal angle. If it they asked to design a unequal angle section, means you have to choose unequal angle section only. If they have not mentioned anything, you have to design as usual as per the requirement. Okay, from that you will be calculating the determine the design strength based upon the TDG, TDN and TDB. Okay, and if the strength obtained from this one is greater than, okay, the factored load, it is okay, well and good. If not, you have to redesign the section. And the last one is what, check the section for slenderness ratio. Now based upon these steps, now we'll try to solve one or two problems. Okay, I will try to start writing from here itself. One problem: design a tension member, design a tension member considering a single angle. Yes, they have mentioned separately that single angle. Okay, single angle section to carry a factored load. They have clearly mentioned about factored tensile force of 250 kilonewtons. The length of the weld is 150 mm. Okay, next take Fy is equals to 250 Newton per mm square and Fu as 410 Newton per mm square, and the length of the member is how much? 3 meters. This is the question given. Okay. Now we'll write the given data here. Factored load given. How much it is? 250 kilonewtons, and Fi is 250 Newton per mm square, and Fu is 410 Newton per mm square, and Lw is what? How much it is? (150 mm), and length of member is. Now why this again newly length of member is given, we'll see in the end. Okay, now what is the purpose of here length given? Now assuming what? Permissible tensile stress. How it is denoted? FTD, which is equals to what? 0.9 into Fi. That is FTD equals to what? 0.9 into 250. Okay, it will be around 225 Newton per 90%, right? 225 Newton per mm square. Okay. Now area required, that is Pu by FTD. What is Pu? 250. It is in kilonewtons. I am multiplying with 10 power 3, you will be getting in newtons, divided by 225. So how much you will be getting? So 250 into e power 3 divided by 225. So you are getting 1111.11 mm square. This is the actual area required. Okay, now I will increase the area by 10%. So increasing the area by 10%, that is 1111.11 into 10%, right? To this one you multiply it 1.10, you will be getting what? 2.22 mm square. Now have they mentioned anything like equal angle or unequal angle? They have not mentioned, right? So for that you can choose any section. So here I am choosing use steel table. Okay, from steel table, so I am choosing the section of ISA 100 by 65 by 8 mm with an area of 1256 mm. See here, exactly this value you can't search, right? So it will be, you have to choose a section which is more than that value. Okay, exact value you won't get any section. So I have chosen a section of 100 by 65 by 8 mm. So I got 1256 square. Now you are ready with the section. Okay, what you have to do now? This is what? 100 mm, and this is what? 65 mm, and this is 8 mm, right? Now this step is completed. This step has been completed, this one completed, and you have chosen the section. What is the next step? determine the design strength TDG, TDN, TDB. Okay, now we'll do it. So first one, design strength of the section selected by one second, right? Design strength of the section selected due to yielding of gross section. Okay, that is TDG, which equals to AG Fi by gamma m naught, right? Now actually from steel table it is AG is already 1256 sorry, so 1256 into 250 divided by gamma m naught, anywhere it is 1.10, it is a standard value. So 1256 into 250 divided by 1.10. So how much you are getting? 285, okay, 0.45 kilonewtons, right? This is due to what? Gross section yielding. Next, design strength due to rupture of critical section, rupture of critical section. So for that, TDN is equals to 0.9 ANC Fu by gamma m1 plus beta AGO Fi by gamma m naught. Okay, so this is a formula. First in this page we'll try to connected link. Okay, so 100 mm is connected, 100 minus 8 by 2 into 8. So how much it is? 96 into 8, 768 mm square. Next, gross area of outstanding leg, that is 65 minus 8 by 2 into 8. So 61 into 8. How much it is? So this is the area. Okay, next we'll solve what is beta. Now what is beta formula? Beta equals to 1.4 minus 0.076 into W by T into what? Fi by Fu into P by LC. Now 1.4 minus 0.076 into what is W? 65 divided by 8 into Fi is 250 by Fu is, I think it is 410 into 65 by, what is the length of weld is given as 150. If I solve this one, 65 by 150 into 250 by 410 into 65 by 8 into, so you are getting how much? 1.23. But whether this value is within the limits or not, you have to check. That is beta minimum, it is always 0.7. What is the formula for beta max? That is Fu, if I am correct, into gamma m naught by Fi by gamma m1. Okay, so what is Fu? 410 into 1.10 divided by 250 into 1.25. Okay, 410 into 1.10, 250 into 1.25. Okay, so you are getting how much? 1.44. So it is more than 0.7 and less than 1.44. Okay, now if I substitute TDN 0.9 into A and C you got as 768, okay, and 410 divided by what? Gamma m1, that is 1.25 plus what is beta? 1.23 into you got this one as what? 468, okay, 488, huh? How much you got? 65 minus 4 into 8, sorry, 488 into 250 divided by 1.10. So 0.9 into 768 into 410 divided by how much? 1.25. So this one is 226.71 kilonewtons plus 1.23 into 488 into 250 divided by how much you are getting? 136.41. So total is how much? 136.41 plus every previous one is, so 363.12. It is what? TDN, right? Next we'll go with the what? Block shear. Design, strength due to block shear, that is TDB. Now here what are the formulas? TDB1 equals to AVG Fy by root 3 into gamma m naught plus 0.9 ATN Fu by gamma m1. This is what? TD1. Next, what is the TDB2? 0.9 AVN Fu by root 3 into gamma m1 plus ATG Fy by gamma m naught. Okay. Now, what are these AVG and AVN equals to area under shear? What we call this as area under shear, okay, which is equals to length of weld into 2 into thickness. So length of weld given as 150. Sometimes they won't give this one. You have to design the welded connection, and from the length you obtain for the side weld, that you have to consider. Okay, in this problem they have mentioned the length of weld. If it is not mentioned, what you have to do? You have to first design the length of welded connection and you have to do the problem. Okay, 150 into 2 into 8. Okay, so 150 into 2 into 8, how much you are getting? So 2400 mm square. Next area under tension, how much? Length of connected leg is 100, okay, into its thickness, how much it is? 800 mm square. Okay, now first we'll do TDB1. What is AVG? 2400 into 250 divided by root 3 into 1.10 plus 0.9 into what is ATN? 800 into 410 divided by 1.25. Okay, we'll solve here. 2400 into 250 divided by root 3 into 1.10. How much you are getting? This is 314.91 kilonewtons plus 0.9 into 800 into 410 divided by 1.25. So total is how much? 236.16 plus 551.07 kilonewtons. This is TDB1 only. Okay, again you have to do it for what? TDB2. What is this? TDB2 is equals to 0.9, yeah, formula here, 0.9 into what is AVG? 2400 into 410 FU divided by root 3 into gamma 1.25 plus 800 into what is Fi? 250 divided by 1.10. Okay, 0.9 into 2400 into 410 divided by root 3 into how much you are getting? 409.04 plus, okay, 800 into 250 divided by it is around 181.81, right? So total is plus 409.04. You will be getting around how much? 590.85 kilonewtons. Now out of this TDB1, TDB2, this one is least. Okay, now I will write these values: TDG, TDN and TDB. What is TDB? Lesser of these two, right? That is 551.07 kilonewtons. This one. Next, TDN 363.12 kilonewtons. Okay, and if I go back once, what is the TDG value you got? 285.45 kilonewtons. 285.45 kilonewtons. Okay, now out of these three, lesser of these three values is considered. So this is the lesser, right? So this is the design tensile strength of a member chosen. What is a member chosen? That is ISA 100 by what? 65 by 8 mm we have chosen, right? Now this is what problem? Design problem. We have to arrive the value, but whether it is safe or not, whether the section chosen is perfect, sufficient or not, how you have to check? You have to compare with the factored load. What is the factored load given? Is 250 kilonewtons. Okay, this is what? PU. What is this? PD. Okay, now since design strength is greater than how much? How I am saying? This is 285.45 kilonewtons, which is greater than 250 kilonewtons. Hence, the section chosen is what? Sufficient to bear the load. What load? Factored load of 250 kilonewtons. This is the statement you have to mentioned. And in the question they have specially mentioned that check for slenderness ratio. Check for slenderness ratio. This is the thing they have mentioned. Okay, now they have given the length of the member as slenderness ratio. What is that? KL by R minimum. They have given the length of the member, right? 3000 divided by R minimum. R minimum you can obtain from what? Steel table. From the steel table you have to obtain, that is 13.9 for the 100 by 65 by 8 mm. Okay, that is 3000 divided by 13.9. So you are getting what? 215.827. Now with what value it has to be compared? We are doing some check, right? That check means what? You have to compare with some value, right? So with what value you are supposed to compare? Okay, with what value means with the value maximum slenderness ratio value, that is 400. Now what is this 400 value? A member which is always under tension. A member which is always under tension will be having a maximum slenderness ratio value of 400. Means in the introduction class we have discussed regarding the what? Maximum slenderness ratio values. What are those? Can you remember? That is, a member which is always under tension will be having a maximum slenderness ratio value of 400, and a member in a roof truss whose reversal of stresses occurs due to wind line and seismic loads having a maximum slenderness ratio value of 350, and a member which is in which reversal of stresses happened not because of wind and earthquake loads will be having a maximum slenderness ratio value of 180. Okay, now here all thing we have done is what? Tensile strength we have calculated. Okay, so you have to check with the 400. So that is the maximum value. We obtained less, so hence our section chosen is perfect. Okay, so this is the design problem for a single angle section connected, right? Now see here, as I have chosen some section, I got this one. It is not compulsory that everyone should get this 285, because design problem, what is the difference between analysis and design means? Analysis, all the members who are doing the problem will be getting the same because already section is mentioned. In the design, what we are doing? You may take some different section, I may take some different section. Okay, suppose here I have taken 100 by 65 by some 8 mm. If I take another one, equal angle means it may pass, but the load carrying capacity may differ. Okay, so that is the reason the design problem values will not be same with the other persons. Even though the question is same, the load is same, but it will be differing. Where it will be differing? It will be differing in the place of choosing the section. Some will take what? Equal angle section, some will take unequal angle section, some will take the percentage of area increment as 10%, some will take 25%, like that it will be varying. So that is the reason the design problem, okay, while evaluation or valuation, the procedure will carry the marks, whereas analysis along with the procedure, the answer is the final. Here in the design, the procedure is very important. Okay, so that is the problem. And in the next class, next session, we'll try to solve double angle section. Okay, one double angle section problem. Okay, and we'll wind up with this chapter. Okay, and what questions you may expect from this topic is, as per the curriculum based, one short answer and one long answer you expect. Short answer will be from the introduction topic, different forms of tension members. Okay, and what we have seen, different forms of tension members, applications. Okay, just 3 marks problems we have discussed, right? That will be the short marks. Okay, that is for 3 marks. And coming to the one problem will be there from the essay type, that may be analysis or design. Mostly design will be asked. Okay, mostly design will be asked, that you have to do trial and error method. As I said you, suppose here you obtain as 285, which is okay, means the section has been chosen is perfect. If it is got, means here the value you got is lesser than 250, means what you have to do, you have to start your procedure once again from where, which step, from this step, means again you have to choose the section, revise the section, since it is not meeting the thing what you have done. You have chosen, you have increased the area, everything you have done, but the thing is what, at the time of arrival, what, the least value is lesser than the factored load. In those situations, what you have to do, redesign the section. For redesigning, what you have to do, after this one, you have to again choose the section, revise the section, means instead of taking here unequal, you go for equal and more some area, you increase the area and do the problem, such that you obtain the value which is greater than the factored load. After arriving the load greater than the factored load only, then our condition is been satisfied. Okay, so this is the double angle section design, single angle section design problem. Next, double angle section, what will be the different from this problem? The load whatever you have given here 250, that has to be made half. The design steps for tension member, this is single angle. Now what will be there for double angle, means the area, the load given has to be half it, since while choosing the section in the table book you won't get double angle section value. For that reason, first what you have to do, you have to design the section for half of the load given for choosing the section. After choosing the section, you make it double, that's all. Got my point? That is, suppose here 250 kilonewtons is given, but he asked to design for a what? Double angle. Okay, for that what you have to do, you have to divide the area by 2. So here what happens, you have to do 250 by 2 means how much it is, 125. For that 125, what is the area required, you calculate. Okay, you choose the section and make it double. Like that, the procedure, everything will be same, means what, area will be same, sorry, next everything will be same. Got my point? So that is the only difference between the what, single angle section and double angle section design. Is it okay? I hope you understood my way of explanation, the single angle section and double angle section. Okay, and next, after obtaining here the value in double angle section, you double it, so that whatever the factored load you got, whether you are satisfying or not, you have to check. If not, you have to redesign. This is the simple procedure which is very, very important. Okay, and thank you for watching my video. Please do watch my videos in a series. I am uploading it with a date wise, okay, some topic wise and date wise. So if you follow the sequence, you can understand the classes clearly. Suppose if you start today, don't watch today's video directly, you go with the design of tension members previous values, previous one, so that you can easily understand the link between the first chapter to today's chapter like that. Okay, thank you.